So today we will discuss about Newton laws of motion. Newton laws of motion. So we understand there are three Newton laws of motion. Okay. So law number one. Law number one. What is law number one? Law number one means unless an external force is exerted on an object or system of objects, yeah, the object or system of objects remain at rest or move with a constant speed. They remain at rest or will have a constant motion, will have a motion with constant velocity, will have a motion with constant velocity. Okay, so now we'll try to understand the physics behind it. Suppose there is an object, right? So from the birth of this object is at rest, so that means no speed, right? We are not applying any force. That means force is zero. This force should be an external force. We will discuss that later. However, the external force is zero. So when the external force is zero, so that means there is no external forces acting on this mass m. So then this remains at rest. So that means speed is zero. That's what it says. Or you have a mass. From birth of the mass, you can think in that way. This mass has a speed u, right? So now this is moving. When this is moving in this direction, it comes to this situation, right? Now what this law says, the speed is still u. So if you think about the time, suppose time is equal to 0 here, 0 seconds. So time is equal to t seconds. That means any time value, right? So this speed is going to be the same. Okay, so this is what the law number one says. I'll show you one example where we see this all the time in VCE physics. You know circular motion. Think about circular motion, right? Example. So if you think about the circular motion, this mass is circulating, right, with speed v. Suppose the speed is v, right? So when it is having a circular motion, there is a centripetal force towards the center, acting towards the center, Fc. Now you will see that these two quantities are perpendicular to each other. Understand this very carefully. Then after some time it moves here, right? After some time it moves here. When it moves there, still the speed is going to be v, the same v as before. The reason? There is no external force acting on it to change the speed. Now you might argue that there is a centripetal force acting on it. Why you are saying there is no force? This is an external force acting on this towards the center, right? But why you are saying there is no force acting on it? There is a force acting on it. However, there is exception. If that force is perpendicular to the direction of the velocity, this speed or the velocity is not changing here. The speed is not changing here. Okay. So here the speed is not changing. Why the speed is not changing? There is no force acting towards the direction of the speed. If there is a force like this or like this towards the direction of the speed, then it is changing, right? So again, I'm saying if there is a force given to this mass like this, then at this point the speed is going to be v1. It is changing. Why? Because there is a force acting on that mass in the direction of the speed. However, in this situation, you have the force which is the centripetal force in this case towards the center. So they are those quantities are perpendicular to each other. So there is no effect on this speed by this centripetal force. So conclusion is, to have a change in speed, the applied external force should be in the direction, or should have a contribution to the direction of the motion. So this is a very famous example in circular motion. Okay. So now this is about law number 1. Let's talk about law number 3. Law number 3. So this is very famous. It says every action has an equal and opposite reaction. Every action has an equal and opposite reaction. Okay, every action has an equal and opposite reaction. Now there are a few common examples here. I'll show you that. Suppose you have a ground and then you are going to put an object on that. So the mass of this object is m. Okay. So gravity is vertically down. So now to see the physics inside this, I'm going to enlarge this, right? So if I enlarge this, the object I'm going to separate from the flow so that we can see the forces acting on it, right? Now when they are touching each other, right? So there is a touch, right? There is a support. We call it support force. When they touch only, you get the support force. Now suppose you have the support force here, but I have enlarged it so that we can see the forces acting on that. So there will be a weight force. Okay, there will be a weight force. So because of that weight force, this surface is going to touch on this, and then this surface is going to feel this weight force. So when this surface is going to feel this force, right, that feeling looks like this. So this surface, the ground, will feel a force like this. That is due to the touch. Now what the ground is doing, ground is giving an equal and opposite force on the object, this way. Right? So because of the touch here, this force is sensed by this floor or the ground, and that would be R here. Then what this floor is doing, this floor is going to give an equal and opposite reaction on the object, which is this. So these two are called action and reaction. Okay? Action and reaction. Now, the best part is this. So when you keep this object on the floor, this object is not going to move, right? Not moving. This object is not moving. If this object is not moving, that will tell you the forces are equal to each other, right? So you understand this is a force, right? These are forces. So if this is not moving, the forces are equal to each other. So we can say R force is equal to W. So what R force we are looking at? This R is nothing but this. This W is nothing but this, right? So force equilibrium is used to this object. Now we understand that the same R is appearing here as well as here, right? So you can say that these are also W and these are also W. So that's how we say that R is equal to W when the system is at equilibrium. Okay, so far we have discussed about law number 1 and law number 3. Next one would be Newton law number 2. Right? So law number 2. Now before I explain law number 2, I will explain some physical quantities, right? Some quantities defined in math, defined in physics. There is a quantity called momentum, right? Momentum is defined by P. The definition of this P is mass times speed. Mass times speed. Right? So this is a derived quantity. You can't feel the momentum. You can feel the mass. You can feel the speed. But mass times speed, this momentum you can't feel. It's a derived quantity. Right? So we call it derived quantity. Okay. Now, change in momentum. Right? Let's think about change in momentum now. What is change in momentum? Change in momentum is delta P. Change in moment. Change is defined by delta in math. So this can be written as delta mv. Okay, you can see P is mv from here. Now m is what? M is mass, right? Suppose mass is constant for object, right? Suppose m, mass, is constant. For an object. So if that happens, we can do the following. Delta P is equal to delta mv. If mass is constant, you can take that out. So if you pull it out, so m times delta V. Now, what is delta V? Delta V in this case, change in speed. Change in speed, right? So change in speed multiplied with the mass is called the momentum change. Let's discuss a question, right? Now diagrammatically I will give you that. Suppose at the beginning means t is equal to 0 seconds, right? Think about a mass m. Suppose the initial speed, initial means what? Initial means time 0. Initial means time 0. Initial speed is u. Okay. Then after some time, right? After some time, that means t is equal to t seconds. T can be 5 seconds, 10 seconds, like that, right? After some time, the speed is going to be v. Suppose this v is greater than u. Suppose V is greater than U. Now slowly I am going to teach you the physics behind it. Now, what is Newton's first law? Newton's first law says, if there is no external force acting externally, if there is no external force, this U is maintained. That means when it comes here, it is going to be U. When it is coming here, it's again U. When it comes to here, it should be U, right? If there is no external force. However, in this case, we have a speed V which is greater than U. So that means this value is greater than this value. So that tells you that there should be an external force acting on it. So there should be an external force acting on it. So that you should know, right? So there is an external force acting throughout the journey, right? So there is external force. I would say F external for now, right? So keep that in the background. Now, if you think about the physics of this motion, right, you will identify what we can see. First thing, there should be an external force. There should be an external force. That is the first thing. Second thing would be final speed is greater than initial speed. So that means V is greater than U. Final speed is greater than initial speed. So this tells you that there is a delta V, change in speed. So that would be V minus U, correct. Now we understand in this system mass is constant. Mass is constant. Mass is M. Okay. So here mass is a constant. So if mass is a constant and there is a speed difference, right? So mass is a constant, there is a speed difference delta V. So that can be written as M times V minus U, right? So this is nothing but delta P now. So we have to understand in this system there is a momentum difference, right? In this system there is a momentum difference. If you carefully look into this equation, you can see momentum difference exists if there is a speed difference. Delta P exists when delta V exists, right? So if you have a system, right? So if you have a system like this, M here, initial speed is U, and final speed also U. Now for this case, so let me say t is equal to 0 and t is equal to t. In this case, you don't have delta U or delta V or delta V, doesn't matter. Delta V, there is no speed difference or velocity difference. So if you don't have a velocity difference, right, this will tell you that there is no momentum difference. There is no momentum difference. Right, so now this we understood. Now summary would be delta P is not is equal to 0, right? When this happens, delta V is not is equal to 0. So now you can visualize the picture, right? So delta V not is equal to 0 means the speed difference exists. If speed difference exists or momentum difference is not 0, this tells you that there should be a force. There should be a force. Because that force pushed the object so that there will be a speed difference. Because of that, there is a momentum difference. Easy. This is the first one. Second one, when delta P is equal to 0, when delta P is equal to 0, that means delta V should be equal to 0. That means there is no speed difference or velocity difference. This tells you that there shouldn't be a force. There shouldn't be an external force. So this should be pretty clear. Now let's understand what is the definition of Newton's second law. What is the definition of Newton's second law? Right? Newton's second law says rate of change of linear momentum. Rate of change of linear momentum. Linear momentum is directly proportional to the applied external force. Applied external force. So that means mathematically applied external force, F external, proportional to rate of change of, this word is very important, rate of change of means delta P divided by delta T. Rate of change of momentum. If you think about mathematically, F external is proportional to ddt of P. Okay. So in BC physics, we don't go with the calculus. However, if you know calculus, it's very easy to understand. Okay, so we go with delta P divided by delta T. Okay. Okay. Yeah. Any questions? Okay, so I'm going to explain this example. Suppose there is object mass m, right? So I'm going to give the detail here. Mass m is equal to 10 kilogram. There is an external force applied to this one. Suppose this force is 10 to the power 3 Newton, right? Then it is starting from u, let's say 10 ms minus 1, right? So at t is equal to 0. After some time means t is equal to t, right? It comes to this situation where the final speed we don't know. The question is, find the final speed. Okay. Find the final speed, v. Find the speed v after 10 seconds. So that means this t is considered to be 10. Okay. So how to do this one? Now You understand there is external force and mass is given. So if there is external force and if there is a mass, there is acceleration. From initial to final, there is acceleration. Due to that acceleration, there is a speed difference. That physics you understand. So now I'm going to use F is equal to ma to this object, to left to right. So if I use that, your force is 10 to the power 3 newtons, mass is 10 kilogram. You will find out the acceleration. So from here, if you simplify this, acceleration is going to be 10 to the power 3 newton divided by 10 kilogram. So this is going to be, acceleration is going to be okay, let me change this a little bit because that's fine. It's just okay, we will live with it. So it's going to be 10 to the power 2. So 10 to the power 2 ms minus 2. That's acceleration. Okay. Now once you find the acceleration is 100 ms minus 2, right? Once you find the acceleration, you can find the final speed, because the definition of acceleration is v2 minus v1 divided by t2 minus t1. So acceleration is 10 to the power 2. v2 is what we need to find. So this is nothing but v2 over here. v1 is given to you, which is 10. Then t2 is 10. t1 is 0. Okay. So from here, you can get 10 to the power 3 is equal to v2 minus 10. So from here you can get v2 to be 10 to the power 3 plus 10. So that should be 10 to the power 3 is 1000, 1010 ms minus 1 for this example question. Okay, let's go with another question. So think about you are going to keep an object in the space, right? So near to the Earth's surface, where the gravitational acceleration is g. G is 9.81 ms minus 2. So the mass here, suppose the mass here is m, 10 kilogram. Okay, so what will happen when you just place mass, 10 kilogram mass, in space where the gravitational acceleration is existing? Obviously you can see this is a acceleration, this is mass, so you will get a force. Why? Because m times acceleration is a force, right? So you get a force, and that would be, in this case, a is going to be g, so mg is force. There is a force acting downward direction, that is called the weight force. So this is W. So that's why in space, when you have an object in space with mass m, you can say the weight of that would be mg, and the unit is newtons. That's a force, right? Sometimes people call it gravitational force. Doesn't really matter how you call it, but we have to understand the physics behind it. Let me discuss another question. Suppose you have a slant path where this angle is theta. You are going to keep an object here, right? You are going to keep object here. Now this is in the free space, right? So this is in the space, you put it on the surface. The mass is m. Gravitational acceleration is always g in the down direction, vertically down. So now you understand, here you get mg. You must get mg in the vertical down direction. Why? Because of the definition of ma, and in presence of m in the gravitational field, so you should get it. So that is fg, right? However, you will understand the motion is in this direction. The motion is in this direction. Motion. If the motion is in that direction, there should be a force in that direction. That is common sense. Right? There should be a force in that direction, then only there is a direction in that motion, right? So that means there should be a force in that direction. There should be force. Suppose that force is force F1, for example. Right? How do you find that force? What we are going to do is, we are going to resolve, this is the only force. Now, this is the only force which you can see. However, if you want to derive this force, we call it pulling force. If this object is pulled in this direction, only there will be a motion in that direction. So there should be a pulling force. That pulling force is derived from this mg, right? How do you get it? Now you're going to resolve it, right? This resolving part I taught you in the previous lesson where I was teaching the projectile motion. So geometrically, this angle is going to be theta. If that is theta, right? If that is theta, you can say this force to be mg cos theta when you resolve. I told you when you resolve towards the angle, it's cos. Then F1 is nothing but mg sin theta. Mg sin theta. Now these two forces are perpendicular to each other. Those two forces are perpendicular to each other. That's how we derive, or that's how we resolve, right? So now you can see F1 is mg sin theta. Now we are going to use F is equal to ma in the direction of the motion. In the direction of the motion. In this direction. Why we use F is equal to ma in the direction of the motion? The reason we have to slowly understand. So acceleration is what you are going to have in this direction. Force is F1. This F1 force. Now we use F is equal to ma in the direction of the motion. So the motion is in this direction. Now you can see mg here, you can see mg cos theta here, you can see mg sin theta here. However, this object moves in this direction. That moves in that direction because of this F1. So we use F is equal to ma to this scenario. So we use F is equal to ma in the direction of the motion. In the direction of the motion. Okay, so that would be F1 is equal to m, mass is not going to be changed. A would be what we need to figure out. So F1 is mg sin theta. We resolved that and found it, and that would be is equal to ma. So the acceleration became g sin theta. Acceleration became g sin theta. That's the answer. And this acceleration is acting along the plane. Now the summary of the discussion. Summary of the discussion is, when you have object on a slant plane, there is a force acting which is F1 in this direction. Due to this, there will be a motion, right? So we use F is equal to ma in that direction. Why? In that direction only the motion is happening. Now if the motion is in that direction, force F1 is in that direction, then acceleration should be in that direction as well. Now, if you go to your previous example over here, you can see when there is a force, acceleration also in that direction, right? Now using F is equal to ma, what we found was what we found was this acceleration to be g sine theta. That is what we understood. So g in this case is the gravitational acceleration in vertically down direction. Sine theta would be the angle with the horizontal direction, right? So that's how you find the acceleration.